Welcome to the AI Research Roundup, everyone. I'm Alex. Today, we're looking at erasing without remembering, safeguarding knowledge forgetting in large language models, published February 27th, 2025. This paper tackles a key challenge, ensuring LLMs truly forget information, not just specific phrases. The authors point out that current methods for machine unlearning, which is about removing specific data from trained models, often only erase exact expressions. They introduce UGBENCH, a new benchmark to evaluate this, and PERMU, a method to improve the generalization of unlearning, making sure the forgetting extends to related ideas. Alright, and it's great to see they've also released the code for this work, so you can find their UGBENCH repository on GitHub. This repository is the official implementation, and as we mentioned, UGBENCH is a benchmark, specifically for LLM machine unlearning. You'll find the code there, evaluation scripts for various methods, and, well, instructions to reproduce their findings. Alright, and this first figure, figure 1, really helps visualize the core challenge these researchers are addressing with UGBENCH. It shows that machine unlearning, at the top, aims to make a model forget a specific answer, but the unlearning scope illustrated below is the crucial part. This scope is shown in a semantic embedding space, essentially a map where related concepts are close. The goal is to forget not just the exact sample, but also rephrased questions, reversed relations, and even knowledge derived through one-hop reasoning that's inferring something in a single logical step, all while keeping unrelated information safe. This really highlights the generalization problem they're tackling. Okay, so this next table, Table 1, gives us a look at the actual data UGBENCH uses. It details the data splits and statistics for the different data sets they employ, specifically TOFU, Harry Potter, and ZSRE. For each, it shows how many samples are designated for forget, meaning these are the pieces of information the model should unlearn, and how many are for retain, which is crucial for checking that the model doesn't forget useful, unrelated knowledge. We can see for ZSRE, for instance, they specifically break down the forget samples into categories like inverse relation and one-hop, which directly test that generalization of forgetting we were just talking about. Okay, so figure 2 here shows us one of the reasons why current unlearning methods struggle with generalization. These plots show the rank of the first key token of the correct answer across the different layers of the model for models fine-tuned with gradient ascent. Gradient ascent in this context is a training technique that tries to maximize the probability of a certain output. So here, it's essentially trying to make the model more likely to produce the unwanted answer. What's really telling is that the rank of this key token, indicating how likely the model is to pick it, rises rapidly in the mid-layers. This happens for both the Harry Potter dataset with the Phi model in A and the TOFU dataset with Llama 2 in B, suggesting the knowledge isn't truly erased. Alright, so building on that observation about mid-layer activity, Figure 3 gives us a different perspective. These heat maps visualize the model sensitivity metric, or MSM, for each token across all the model layers. The model sensitivity metric is a measure these researchers developed to quantify how much the model's output changes when a specific token in the input is altered. And what's really clear here is that subject words like Dumbledore or Methley or Jordan Sinclair show much higher model sensitivity metric values, indicated by those brighter, warmer colors, especially again in those mid-layers. This suggests the model is particularly sensitive to these subject tokens. Okay, so building on that insight about model sensitivity, Table 2 here shows how PERMU, their proposed method, performs on the TOFU dataset against other methods. For the forget data, PERMU achieves a big drop in forget probability. That's the chance it outputs the forgotten fact, from around 78% for some baselines down to 39% with PERMU. It also boosts the forget truth ratio to over 64%, meaning more truthful, non-forgotten answers are given. And importantly, PERMU does this while maintaining the highest model utility, or MU, so it still performs well on useful retained knowledge and gets the best forget-retain trade-off, or FRT, a new metric balancing these two aspects. Alright, Figure 4 here really shows PERMU's core mechanism. Part A, the clean run, shows the model correctly answering soccer with high probability for a query about Messi, and its rank as a prediction improves through the layers. Then, part B, the corrupted run, perturbs the input embeddings for Lionel Messi. Input embeddings. These are rich numerical representations of words, enabling the model to process language. This corruption causes recall failure. Soccer's probability plummets, and its rank stays poor. PERMU leverages this contrast between the clean and corrupted outputs to achieve unlearning. PERMU's approach of contrasting these clean and corrupted runs, specifically by looking at how those input embeddings influence recall, really offers a clever way to achieve targeted forgetting. It's a key step towards safeguarding knowledge in LLMs, ensuring they don't reveal unwanted information while still remaining broadly useful. This kind of control is crucial for developing more reliable AI. Well, that's all for this AI Research Roundup. Thanks for tuning in. I'm Alex.